We come to you talking from the open source satellite program, where we want to make space more accessible through the development of an open source microsat platform and community. We do a series of talks once a month. It's about the cadence we like to do on a wide range of topics. So I'm a system engineer working on the open source satellite program. I'm working at KISP, doing system engineering and a whole range of things. And one thing that I do as a system engineer quite a lot is power modeling and also delta V and drag modeling, looking at end of life and maintenance and things like that. So that's where I come across solar activity, and so why I've got a bit of an interest in it. So what am I going to cover? I'm going to talk about what solar activity is and the solar cycle and predicting the future. I said as a system engineer, I'm looking at things like deorbiting satellites, orbit maintenance, etc. And actually understanding what's happening with the solar cycle is quite good to know and is involved in some of the modelling that I do. So understanding, predicting the future of solar cycles is quite important. And then I'll go on to why it is important. Okay, so, and there's another picture of the sun taken very recently. So, solar activity. So we look up into the sky, and when we actually get to see the sun, which obviously at this time of year isn't as often as we'd like, it feels fairly constant, and it doesn't feel like it's varying a huge amount. But the sun does show periodic variation in activity, and that variation was first postulated back in 1761, with the first solar cycle first being identified in 1843. So we've been monitoring the sun for quite a long time. And in 1852, the first numbered solar cycle was designated as starting in 1755, based on earlier observations. So we've been counting solar cycles since 1852. But we can do even more than that in terms of understanding what's been happening in the sun by using carbon-14 radioisotope ratio measurements. It's also been possible to reconstruct the solar cycles for the last 11,000 years. So we've been monitoring the sun and what it's doing for quite a long time. And just as an illustration, here on the right, I've got a couple of videos of the sun. So the top one was taken on the 17th of January this year. And then the bottom one was taken in mid-July in 2019. And I hope you can see and agree with me, there's quite a big difference between these two images. The top one is showing quite a lot of activity, coronal loops and things like that, and flary type activity, whereas the bottom one looks very, very quiet. And the significance of the dates when I took these will become apparent as I go through. We want to have an open discussion session about the space industry and getting into the space industry. I'm really lucky to be joined by a couple of guest speakers. So I've got with me Heidi Tiemann from the Space Skills Alliance, who's going to be talking about space skills. And I've also got Kathy Bowden from the Space Catapult, who is going to talk about the SPIN program, the Space Placements in Industry program. So I'm really delighted to welcome them both onto the call today.
So I thought start with just covering a few of the skills gaps in the current space workforce. And the overview really is that the majority of companies are saying we are seeing skills gaps in job applicants, and about half the companies saying we have some sort of skills gaps in our current workforce. This means that when people are applying for jobs, they may not have the skills or competencies required by the company, and those in the workforce maybe aren't upskilling as quickly as the companies requiring them to for certain projects. So if we have a look at this kind of graph, this shows the overall breakdown of some kind of broad areas of skills gaps in the space industry. So this is for the current workforce, and about 60% of businesses were saying, look, about 50% of businesses saying we've got skills gaps in the current workforce. And the majority of them are saying, look, that's in the software and data side of things, or commercial operations, the business aspect.
The skill set I feel is important for a software engineer in the space industry would, as well as your technical skills and your ability to to take in complex ideas, is also the multidisciplinary aspect, because in the space industry you're writing software for hardware, so that's very embedded stuff. So you've got to have understanding of the electronics to some degree, and be able to read schematics. You've also got, as well as going with the multidisciplinary side, you've also got to be able to communicate with other members of the team, so like systems engineers and electronics engineers, to be able to all come together, because you're really bringing all these different skill sets together to create one end product, which is your satellite solution. So everyone needs to work together, otherwise it's not going to go as well.
I'm responsible for overseeing all administrative activities that facilitate the smooth running of the office, along with supporting the team and the managing director. For example, I coordinate all travel and event administration. I support with the recruitment of new staff, issuing contracts. I oversee the finance and accounts duties such as expenses, sales invoicing, accounts payable, preparing payroll, reviewing business insurance. Then we have the HR side, the staff development, the policies, procedures, and all of these tasks are essential for the general day-to-day running of the office, along with being a key point of contact for my colleagues.
You need to be organised in your work and have a rigorous approach with attention to detail. This allows you to deal with the stringent requirements and consider multiple what-if aspects. This is all aimed at ensuring maximum reliability for the finished product, because you can't send a repairman to fix a satellite. You also need a reasonably wide skill set to cater for the range of design requirements already mentioned, along with additional aspects like EMC. Hence, versatility is very important. You also need to be a good team player, because there is significant interaction between colleagues who may be working in different disciplines. The willingness to learn and adapt is particularly important, but there is plenty of opportunity to learn from more experienced peers. And finally, and most important, you need to have an interest and enthusiasm for the role.
So say someone is just like, oh, I'm really interested. I'd love to be involved in looking at how, say, space sustainability works, and doing some sort of the research and things that you guys do. What would you, is there like I know there's never one size fits all path into these things, but is there sort of a particular route that you might suggest to someone, or things they should maybe look at, or paths they could explore to work in this area?
Yeah, of course. I think actually the first thing I'll say is that all sorts of different disciplines are needed.
Mm-hmm.
So you don't have to be an engineer. You can be an artist. You can be a writer. A scientist, a teacher. All these different disciplines and roles are absolutely fundamental to us solving these kind of problems. These kind of societal problems, and space debris, space sustainability is counted amongst those. Requires the combined effort,
Mm-hmm.
A community effort to solve them. So it doesn't really matter what your interests are in terms of the type of job that you want to do, and so on. But what I would say is that that solving these problems does require an openness,
Mm-hmm.
I think, to a certain extent, and thinking beyond your discipline, I think, which can be a bit of a challenge. But then you become, if you like, the perfectly fitting jigsaw piece, puzzle piece, because you kind of fit into the bigger picture in that sense. I think if you work in a silo, it becomes very difficult then to sit alongside a lawyer and to figure out. So it's not about learning the law.
Mm-hmm.
It's about that openness and willingness to work alongside them, and so on. I think that quality, more than anything, that ability to be work in a multidisciplinary way is kind of what's needed, regardless of whatever discipline it is that you're in.
Well, I think that ties really nicely, because this is effectively, we need people to work together to solve the problems, don't we? So to have that ability at that kind of smaller level, to then be able to bring that out into the wider level, is it pans, doesn't it? So that makes sense.
Yeah. But also I think it's a willingness to listen to the other side. sometimes we're so focused on what we do and defending what we do that we're not necessarily willing to understand that there's another perspective on the same issue that is also legitimate. I think, and I would tend to look at these things as a circle. I sit on one side of a circle. There's always going to be somebody sitting on the other side of that circle. No matter where you are on it, there's always that other side. I think just be willing to listen. I think, my career has taught me that, working in academia and working in the different roles I've done as giving that, I think, just awareness that I'm not always, I may be right in what I'm saying, but it's not always the exclusive position. There's always going to be a different perspective, and I think I just got to be open to that.
And I guess like compromise isn't always a dirty word and doesn't always mean that you failed. Actually, there's that big, like you're saying, that bigger picture piece that actually some compromises on multiple sides gives you a better overall, result than actually being fair. Because I mean, I'm an engineer, so I hold my hand up and I'm like, but my thing is the best widget that's ever been made, and why would I possibly want to change it? Oh, because actually I'm not the only thing that has to operate in this ecosystem. And I think I mean, I'm sometimes you get quite, like you say, quite siloed, quite focused on your objectives, and it can be hard to focus on that bigger picture piece. I think especially because sometimes these problems feel so big. It's a bit like sometimes we talk about climate change, you go like, oh golly, is my me doing my recycling or putting my glass in the is that really going to make a bigger picture change? And I think it's that appreciation. Little bits actually incrementally do help as well, right? You don't have to be able to solve the whole problem, but taking some steps is important.
Yeah, indeed. I think you're absolutely right. I think one of the philosophies I had, I take a lot from movies, by the way. I think movies are kind of, and books, really good expressions of humanity. The film The Martian, I'm probably going to ruin it for people who've not seen it, but right at the end of the film.
Spoiler alert here.
Right at the end of the film, talking about, solving problems. You solve the first problem and then you move on to the next. And you just keep doing that until you end up meeting your goal. And I think that's a really powerful message. In a sense, you don't need to solve the whole thing immediately. You solve things one step at a time. I think in terms of space sustainability, we're probably on step 1 or 2 out of tens or hundreds of steps that we've got to get through before we can look at the space environment and say, we've figured that out and we've solved it. But that doesn't mean to say we should stop, because it's so far off and it's so big. We just keep solving those problems.
We're some space people, as in we're not going to space, but we are in the space industry. And we're also software engineers, embedded software engineers. So we write software for the embedded systems on board spacecraft. If I had to do a kind of top 3 processors of the 3 that we chose. So, usually these microcontrollers are a little chip, a little square, a bit like that. Can be like that. Probably can be like that as well. But anyway, most of them have like embedded flash memory, embedded SRAM, cache memory, lots of peripherals, not profiteroles, peripherals. Arrays of flash memory. What actually happens is it sets all of the content of all the cells to 1. Okay? 1, 1, 1, 1, 1. I've got a friend actually, she finds it funny that I talk in binary, but she's in marketing. And if she ever sees this video, she'll be like, oh my goodness, you actually did a podcast where you spoke in binary? Who are you?
One day he decided to turn the cache off. And this fixed it. Wow. Why would it do that, you ask? Well, first, let me explain to you what cache is.
Cache.
So, you could probably guess what the problem was, but it took me a while to figure out.
Hang on. Can you guess?
Can you guess?
We have like some kind of like questions going on. Right, well, what can we conclude? If in doubt, turn off the cache.
Yes, it solved a lot of problems for us.
Well, unless you need the cache, in which case leave it on and then solve the problem another way. If you are, in the very niche group of people worldwide who want to use ARM processors in space, there's probably, how many people are there like that? How many people do you reckon?
No, not.
A couple of thousand.
Perhaps we could just start with who you are and why space is such an important topic for you. What was that thing that sparked your interest?
Well, I think that space is attractive to a lot of engineers and enthusiasts, and I had a healthy appreciation for space and the achievements in space and the technology that comes from it. Um, growing up. But one of my first jobs was fortunate enough to be able to work on a communication satellite project, and this was a big transition for me, coming from a part of the country in the United States that did not have any space activity to speak of, Arkansas, and moving to California and working at Globalstar, at Qualcomm. And wow, was it a revelatory thing in many ways. And so I started to look at the differences in communications terrestrially versus the communications in space, and realized that there was significant differences, but a lot of overlap. And that's really what kind of the interest in space. As soon as I kind of developed an appreciation for the amateur, especially amateur radio satellite achievements in space, and the longevity and the history, how long it had been a part of the sort of achievements in space since the very beginning, I started to get more and more involved, and tried to bring open source into that practice. So tried to bring more open source work into amateur radio satellite work, which was not an easy thing to do. And so that's kind of the sort of where I'm coming from, and how I came to be a space enthusiast and to do work, technical work and regulatory work for space.
This month, we're going to hear from our Spinterns, space placements in industry interns, who are currently halfway through their 8-week internships. We'll hear what they've been up to so far in each of their projects and what progress they've each made. First up, we have James and his project, Open Source Satellite Ground Station Development.
So my Spinternship has been about building on the work that has already been done on open source ground station components. So these are the bits that sit on the Earth. So they're the kind of the Earth side of the gear, and we use them to talk to satellites in orbit, send them telecommands, and receive data back from them, both the payloads and just general data for the satellite. So I'll get started. So my objectives for this project, I was supposed to architect a small scale ground station which can run on something like a Raspberry Pi. So cheap and cheerful hardware which kind of a university or school or university society, something like that, can easily get their hands on. Because I imagine there's going to be a lot of university and school involvement with OSSAT projects in the future. So I'm also going to build a working demo of a ground station. So that's kind of the whole computer tracking system, with a rotator as well. So there will actually be something which is capable of pointing at satellites, and their ASL stands for azimuth and elevation, which are the kind of the 2 degrees of freedom of that you need to be able to track things across the sky. So at the bottom, we have this satellite, which is moving in the satellite dish, which is moving in the azimuth direction, and then this giant ESA satellite, which is moving in the elevation position. And then you also sometimes get these spooky domes, but those just have satellite dishes inside them, and then you can't see where they're pointing. So and those are mostly used for kind of more professional and military installations. And then I was also meant to produce some instructions and documentation so everyone can repeat my work, and what I've done doesn't get lost, essentially. In addition to this, kind of an extra goal was implement a SDR-based modem, and I'll be explaining what all of those words mean in the next few slides. So on to some of the research which I've done for this. I think I spent about a week and a half doing purely research, and then there's been quite a bit going on as I've understood the brief and the project better and padded out what I'm going to do. So orbits and TLEs. So when you put stuff into space, it tends to move, which can be quite hard if you want to communicate with it. There's definitely some challenges there. So it means the whatever ground apparatus you have with the antennas is going to need to move and follow the device and follow the spacecraft. And one of the ways we do this is with TLEs.
Next up, we have Harvey and his project, STM32 Onboard Computer Arduino Integrated Development Environment.
As a little introduction to my internship, I'm looking at using an STM32 chip on making sure that we can use it within Arduino's integrated development environment. So basically, we want to create some kind of documentation and some actual files and some profiles for certain boards that we can use in the Arduino IDE. And there's a few different variants of a certain type of chip, which makes stuff very easy because you can just build upon one chip, kind of change it out. So the reason you actually want to use the Arduino IDE is it does just make it a little bit easier to program these chips. It just makes it easier to see the code. It's all in one place, and it's not as confusing as potentially some other environments. And again, so just by doing this, it helps speed up testing, development, prototyping, just to keep everything a bit easy, and then you can just get it done quite quickly. When it comes to actual kind of flight software or testing, that will be handled by different programs that go into a lot more detail. But in terms of just on the desk, you want to do a proof of concept, it's a really good tool. So just to kind of reduce all of that to the main objectives is to create a custom board manager for the boards that we want and to the needs that we want to use the boards for. And we want this manager to create the code, compile it, and upload it to the chip. So it just handles it for us. Don't want to have to keep using different files going between programs. We want it to just be a click of a button. And also write some example code and libraries that introduces you to using some of the terms in Arduino, or have some nice libraries and some code that can do some complicated stuff for you in just a few lines, which just helps with testing. So overall, my actual plan broken down for the project is kind of split up into the weeks. I have missed a little bit, so I'd like to say I'm kind of in week 3 of the work. So again, like James, for the first kind of week or 2, it was more just a bit of research, understanding how do you actually do this, because it's very easy to use, but it's quite complicated to kind of create yourself from scratch. And then just reviewing that chip, like I said before, that's on quite a few boards, and kind of understanding what it can do, why do we want to use it. And then going forward from now is kind of tailoring the board manager to the actual chips and actual boards that we've got to make use of the stuff that we actually want to make use of. And again, it's just to build upon that to make it for the actual boards, do some testing, and then hopefully finally create a nice kind of polished package that we can push out at the end of it and maintain over a long period of time.
Next up, we have Theo and his project, Signal Acquisition Module Prototype Development.
Hello everyone, I'm Theo and I'm one of the Horizon interns. So my project is to create a signal acquisition prototype. So you might be asking, one sec, what does that actually mean? So hopefully you've all heard of Horizon's Amber constellation. This is planned to be a constellation of dedicated signal intelligence satellites. This would allow for things like economic exclusion zone monitoring, dark ship identification, counter-piracy operations with satellite phone interception, and then rescue and interdiction. The plan is that I will be making a cheaper, well, hopefully cheaper prototype using consumer hardware. And then this would be able to be tacked on to most satellites just to improve coverage. So to be able to do this, my plan is to identify signals of interest and characterize them, design and produce a prototype of the module, and then develop the test procedures needed to validate the prototype, Then I'll be creating some pretty comprehensive documentation with instructions on how to make one from scratch. And then with the time remaining at the end of the internship, I will just be expanding the capabilities of it and refining the design. So I used a lot of pretty ambiguous terms there, so I'm going to take a step back a bit and try to explain some of them now. So in the modern digital world, nearly everything is communicating with something. Your phone will be communicating with local cell towers and will be connected to Wi-Fi. For example, when I'm at uni, I can control my air fryer and my lights with my phone. So signal intelligence is basically just intercepting signals of interest, and signals of interest can be whatever information you want to find out or whatever is relevant to you. Now, I'm not saying that anyone is particularly interested in what I'm telling my air fryer and how to cook my dinner. So this is typically for more major things. So the main examples would be things like AIS from ships, satellite phones, ADS-B signals. I'll touch more on them later, but signal intelligence just improves your situational awareness. This then comes with some commercial and defense applications. Commercially, you'd be mainly looking at, say, improving the efficiency of shipping traffic in built-up areas, and then defense-wise, maybe anti-piracy. So that is the end of the presentation. I've run through that a bit quicker than I thought I would, but thank you all so much for listening.
Lastly, we have Hani and his project, Satellite Signal Acquisition Algorithm Development.
I'm Hani, I'm the other Horizon intern, and my project is Signal Acquisition Algorithm. It sounds really similar to Theo's. That's because two of the three words are the same. I'm the algorithm side, he's prototype. They're two different projects. He's more on the hardware side of creating the hardware to pick up the signals, and I'm more on the software side of simulating signals and then being able to pick those up, both on PC and not like any hardware involvement. But I'll explain more about that in a moment. So there's a lengthy job description that details quite a few different things to consider when carrying out this project. So it talks about familiarizing myself with the software, setting up the test bed, and identifying things that are necessary. That's all pretty similar to what Theo was doing. For the first like week or two, we were both like researching things, sharing some notes sometimes. But it also talks about being able to simulate signals of interest as well as create the software to pick that up and decode it. But I summarized it here in a sentence. Use of software-defined radio hardware and software tools for signal generation and acquisition. So essentially, it's just signal created in PC, sent to a hack RF, which is able to be picked up at another hack RF, which sends it to a PC that it's connected to, which will be able to process that data. So essentially, there's two parts to my project. There's the signal generation, and then there's the signal acquisition. So I'm planning to put both of those into one single piece of software, but essentially have like two modes that you can use depending on what your intention is. In terms of the tools that I used, similar to Theo, I used HackRF and GNU Radio. So the HackRF is a software-defined radio, and you've just heard about that, but I'll explain really quickly. It's essentially a radio transmitter and receiver, a transceiver, which can send radio signals and receive them. And unlike a traditional radio, it uses software rather than electronic components to process the signals.
Welcome, everyone. I'm Ollie, and this is what I got up to in my placement year here at KISS. So I'm going to start off with a section just about me and how I got here, and then I'm going to look at some of my projects, and then I've got an other stuff section. I didn't really think I'd have time to go through everything that I've done in my year, and so I've kind of crammed everything else into an other section at the end. So first, just a little bit about me. So my name's Ollie. I'm studying aerospace engineering at the University of Bristol. So I was looking for placements kind of everywhere. I knew that I wanted to work in the space industry because, well, I've always been into space, kind of all aspects of space, and that's why I started an aerospace engineering course. Yeah, so I was applying to loads of places, and I eventually saw an advert for KISP, and I'd heard of KISP through their involvement with the spaceport Cornwall, and so I was like, oh, that sounds like a really good opportunity. Let's apply there. So I sent in my CV and covering letter, and then had a couple of interviews, and then amazingly on my birthday I got offered the job, which was quite cool. And yeah, here I am. So once I'm finished here, I've got 2 more years left of my degree, and then we'll see what happens next. So now we're going to look at some of the work that I've been doing while I've been here at KISP. So as I'm sure some people are aware, a lot of what I've been doing since Christmas has been on SAT-LL, a training satellite that we're developing. So the idea is that it's a functionally representative model of a satellite. It will do everything a satellite should, but the ways in which it does it are it's not always flight representative. It's maybe in a kind of cheaper, easier, more user-friendly way. And obviously one of the key areas in which it deviates from flight standards is in the structural design, which is where I've done most of my work. So obviously a CubeSat would usually have an aluminium alloy kind of structure, but we couldn't really give SAT-LL that, because then it would cost thousands of pounds just for the structure alone, and no one would buy it. So we knew that we had to have a 3D printed structure so that we could make it quickly and easily in-house using our 3D printers and laser cutters. The design went through a lot of iterations. These might all look quite similar, but each change you have to make kind of 50 other changes. Like you move one thing up and then you have to move everything else down a bit. Then it's a lot of kind of balancing different things. The general principle of having subsystem boards which slot into a backplane kind of remain the same. So you do have these kind of shelves in the structure, but all the stuff around that has kind of changed and been tweaked. As you can see, the height changed quite a bit throughout the process. But eventually we got to this design, which is the current kind of final version. I say final, it probably will change more as we develop other things. But this is where we are at the moment. I've labeled some of the kind of key features on there. I won't go through all of them now, but there's a lot of things here that allow us to demonstrate actual flight functions. We've got like a deployer so that we can demonstrate separation switch functionality. We've got a deployable magnetometer so that we can show a deployable mechanism on a spacecraft. And then we've also got other things which aren't as flight representative, so things like having removable front covers, which are transparent. That's obviously more for the teaching purposes, so that you can take the front covers off, remove boards, test on them individually. And so that's where it kind of deviates from actual satellite. And once we'd come up with the design, we started making it. And it was kind of an iterative process. You'd kind of make things and then think, oh, I've got to tweak that. And so you kind of go back and forth between designing and making. But eventually we got to this final structure, which I actually have here with me now. And it was really good to kind of get a proof of concept of what we designed. We've got some of the kind of mechanisms here showing them working. Got our nice deployable antennas which pop out the sides. Yeah, it's really been quite cool to see it all come together and be involved right from the start through to having an actual thing in front of you that you can hold, and will hopefully be used kind of in the future SAT-LL development. A lot of things, especially when you're manufacturing, there are a lot of things that you maybe don't consider when you're designing. So things like tolerances and stuff. And yeah, ensuring you've left enough, like a big enough hole size to include heat set inserts, and a lot of things that you don't really consider when you're designing, but you have to consider once you actually start manufacturing them. So that's been quite good experience to get.
Hi everyone, my name is Ben Hudson. I'm a systems and AOCS engineer at KISP Space, and I'm working on the open source satellite program. And today I wanted to discuss a presentation that I recently gave at the International Astronautical Congress held in Milan this year. And this is about an autonomous ADCS, so that's attitude determination and control system, an autonomous ADCS commissioning sequence for nadir pointing small satellites. And the idea here is this is applicable to our next generation microsatellite platform that we're developing, which forms a core part of the open source satellite program. So, as has been discussed before on the OSSAT podcast, KISP has identified this gap in the market for a highly performant but low cost small satellite platform. And this is because from our experience with some customer programs, we're finding that CubeSats are increasing in size, but often our customers are suffering from fundamental issues related to the CubeSat standard, the form factor, and sometimes the lack of performance being offered by those. But we also see that small satellites are trying to come down in price to get closer to that of the CubeSats, but are sometimes struggling to do so with their heritage designs and processes. And this is where the NGMP comes in. So the NGMP and the open source satellite, once it is released, will be a highly performant small satellite platform that is closer to the price point of a CubeSat, filling this market need that we have identified and have seen through many customer programs who are driven to the use of CubeSats primarily because of cost and not because of what is what they actually need. So the aim of the NGMP is to significantly reduce the price point of the platform through minimizing things like non-recurrent engineering, touch time of the system during integration and test, and also operational costs. And we can do this because we are starting from a blank piece of paper and can take a more holistic approach to the design. And here you have some key, a description of the key elements of the NGMP. So we have this integrated platform avionics, which is shown on the in the architecture on the right, which minimizes the change required between missions of different applications. So all of the core functionality of the satellite that doesn't need to change on a mission by mission basis is kept within this integrated platform avionics. And that means it's only the peripheral items that may need to change depending on the mission. And we're designing this IPA with the idea in mind that it must service a range of different applications for initially low Earth orbit satellites. And then some other approaches we're going to be taking to reducing the NRE and the overall cost of the program are things like performing automated testing in INT, as this will minimize the touch time required. On the left here, we have the sort of first generation specifications of this platform. So yeah, as you can see, we have this scalable mass range of 25 to 250 kilograms, scalable power provision. So the power system could be increased in size if required by the particular application being serviced. And importantly, this 5 to 7 year lifetime with single point failure tolerance. And as part of reducing the overall mission cost, we have this desire to automate as much of the operations as possible. Now, the launch and early orbit phase has been identified by us as a prime phase of the satellite's lifetime to automate. So as I've just said, the NGMP will be capable of servicing a wide range of applications. And in fact, most satellite applications do actually operate in low Earth orbit and also require a nadir pointing attitude for operation. And by nadir pointing here, I mean a spacecraft that is pointing one of its body axes towards the center of the Earth. And you'll find that most applications need this, whether it be Earth observation, communications, satellites, and lots of others. So although the NGMP will service this wide range of applications, there is no reason why a common launch and early orbit phase approach cannot be implemented if most of these spacecraft require a nadir pointing attitude during nominal operations. And the launch and early orbit phase has some varying definitions, but overall we are thinking about the time here between the satellite being deployed from the launch vehicle, where it will typically be placed in a random tumbling state, through to when it is finally into its nominal attitude and it's ready to begin perhaps finalizing commissioning of the spacecraft and then entering nominal operations. Now, there has been some discussion in literature and by some other organizations regarding automating their LEOP operations, but there are in fact very few descriptions of actually implemented solutions and on-orbit results. And we think this is probably because of both a protection of IP issue, which of course is what we're trying to overcome with the open source satellite program, but also a general difficulty and hesitance to change heritage solutions. If you have a design that already works or has worked in the past, why change it? But we think this can be this can prohibit real development and advancement in technology, and this is of course a problem we do not have as we are starting from this blank piece of paper. So it is certainly an aim of the open source satellite program that will be capable of a greater degree of autonomy than has perhaps been demonstrated in the past. Now, a large portion of the activities required in the launch and early orbit phase are related to the ADCS, so the Asset Determination and Control System. So to constrain this initial problem, here we consider the autonomous commissioning flow just for the ADCS. This is an autonomous solution for getting us from a random tumble from the launch vehicle separation through to nadir pointing. So we're not yet considering the commissioning of the rest of the satellite or of a propulsion system or the payload itself, and we'll consider these things further down the line as the NGMP and the OpenSource satellite program develops. So on screen here is a nice depiction of one of the operations we're performing in the launch early orbit phase, this detumbling phase where we go from this random tumble through to a more controlled spin. And we also have the objectives we're trying to meet with this autonomous commissioning flow. So we want to minimize the time from separation to nominal mission attitude, as any time spent in this phase is not going to be producing any income, any money for the or actually performing the useful application of the satellite. We want to minimize operator intervention required. The LEOP phase is typically very people intensive. It requires lots of communication with the ground, which can be expensive from an operator point of view, and also from just the time of people required to monitor the spacecraft and perform some of these commission activities on the ground. And we also want a deterministic and robust autonomy logic that places the system into a safe state in the event of a failure, as we don't want this autonomous solution to put us into a state where we cannot talk to the spacecraft, or it actually causes a failure in the process of trying to get through to nadir pointing.
Hi, I'm Paul, and
I'm Charlie.
And we're here from the Open Source Satellite Program, where we are trying to design make a design of the next generation micro satellite platform. So it's a spacecraft platform where we'll be open sourcing everything to do with it. So from requirements right the way through to the electronics, computer-aided design, the mechanical design, the software, the VHDL, all the bits that make up a spacecraft. We're going to be open sourcing this design. Been an exciting program I've been involved with for quite a bit of time, and through that journey we've been learning a lot about different aspects of spacecraft design. We've got some experience of doing it ourselves, but through different companies and that kind of thing. So we've come together and we're trying to do this thing that could help to transform the space industry. Learn the lessons from New Space, where we've got the innovation of CubeSats. And we're trying to sort of build upon that and make a spacecraft platform that's slightly larger, more capable than a CubeSat, and make it open source, which is very exciting, very cool. And actually, our kind of function within this organization is with embedded software. So both me and Charlie are both embedded software engineers, and both got a bit of experience of electronics as well. And we're here today to try and demystify some of the things to do with something called CSP, which we'll get into. But when we're not here, there's things that we enjoy doing. We have been known to sort of take to the stage and rock it out. What's your favorite band, Charlie?
Nirvana, of course.
Nirvana, of course, obviously. He's like kind of a bit of a Kurt Cobain lookalike, but we have a go with music and that kind of thing. And certainly when I was in the summer, we managed to get onto the stage at a little sort of music festival thing, and I said to Charlie, right, what should we play? And he said,
Nirvana, of course.
Nirvana, of course. And so I was forced to sing like Kurt Cobain. I'm only 45. That's not necessarily so easy. But we had a great time. Love doing that kind of thing. So that's the kind of thing we do. What other things do we like? We like the pub.
Yeah.
We like the pub. Yeah.
Bit of sports.
Yeah. But we got one of those jobs where actually what we like doing is what we have to do on the day-to-day as well, which is pretty cool actually. And I'm sure a lot of people who are probably watching this video have jobs that are similar to that. So high five to you, high five to us, high five. We got cool jobs, geeky jobs. But if you're a geek job's a cool job. So, there we go. Anyway, why am I wittering on? I don't know. Let me talk about CSP. So what is it? And why am I sat here talking about it? So, as part of the design of the spacecraft, you have to design the communication aspects. So, you know, how is one subsystem within a spacecraft, let's say a power system, how does it talk to another subsystem on the spacecraft? You know, maybe the onboard computer or something like that. How do these things talk together? And what protocol do they use in the communication? Not only that, you know, the spacecraft has also got to communicate with the ground over a radio, and from the ground to the spacecraft. So how does that work? Well, in the new space industry, there's been this invention called CSP, which stands for CubeSat Space Protocol, CSP. And this thing, it describes exactly that. It describes how you would communicate from the ground to the spacecraft, and from the spacecraft to the ground, and also how subsystems on the spacecraft communicate with one another, which all sounds fan-dabby-dozy. And there are other protocols out there. And, you know, the space industry is much like looking out the window in the UK and looking at the weather. It's varied. It's very varied. And, you know, I look out, we're actually in front of a window right now, and I'm looking out and it is very, very gloomy out there. A sort of shade of grey, I would say. And you?
I would say the same. Yeah.
And you know, I might get here tomorrow and look out the window and I might see more grey, quite likely, or I might actually see, you know, sunshine and a cloudless sky.
Very good analogy.
Very good. And the space industry is much like that. New space and the sort of, you know, the more institutional space industry, the ESA, the NASA, they are actually quite different in the way that they deal with things, and particularly when it comes to things like communications protocols.